Our speaker for today's session is Dr. M.S. Santosh. Dr. M.S. Santosh is an experienced researcher, TEDx speaker, educator, and master trainer with a demonstrated history of working in the academic, research, and startup sector. With over 100 publications, his research interests are in the area of hydrogen energy technologies, wastewater treatment, and sustainable material development, and has collaborations spanning different countries and continents. He has successfully completed projects funded by national and international funding agencies, including the European Union. He is a recipient of several national and international awards, such as the Department of Science and Technology, India Young Scientist Award, BRICS Young Scientist Award, Commonwealth and Hungarian Fellowship, Swedish Institute's Guest Scholarship, IUPAC's Junior Research Award. He is a member of the Indian National Young Academy of Sciences, National Academy of Science, and a fellow of the Royal Society of Chemistry. He is also a visiting scientist to CSIR, South Africa, and NUST, Russia. He is currently working as a senior scientist and head of the Coal to Hydrogen Energy for Sustainable Solution Division at CSIR, Central Institute of Mining and Fuel Research, Dhanbad, India. Thank you, Dr. Santosh, for joining us. The stage is all yours.
So, very good morning to all the participants present here and the organizers. Thank you so much, ACS, for inviting me and providing a platform to share my research work on this occasion. It's a great platform to reach out to the global audience and scientific community who are interested in specific scientific areas that keep happening as part of ACS Science Talks from time to time. And today, I'm fortunate to be part of this activity. And I'll be speaking today on how hydrogen's progress, ranging from production to separation to storage, varies, and how we are contributing in those domains. I'll not be focusing more on the production and separation part, although I'll give a small bit of introduction and introduce some basic aspects of our activity. But my stress will be more on the storage component, which is one of our strengths and which is the key activity of our research group. So basically, I'm currently associated with the CSIR, Central Institute of Mining and Fuel Research, which primarily deals with a lot of coal mining related activities and contributes to the mining sector mainly. And also we work in the domains of fuel, ranging from gaseous fuels to liquid fuels like methanol, ethanol, and DME, and including the hydrogen and ammonia as well. So we also try to contribute towards CO2 capture, utilization, storage, where this is one of the upcoming areas where a lot of impetus is given to such CCUS-based mission and activities associated with it. So before going into the actual topic, I would like to just briefly introduce the areas of my research work, what we focus on. We call our division as CHESS in abbreviation, which stands for Coal to Hydrogen Energy for Sustainable Solutions. And this CHESS division focuses primarily on hydrogen production by developing electrocatalysts, hydrogen separation by developing membranes suitable for separation of hydrogen exclusively. We work on hydrogen storage, where we emphasize more on the development of composite pressure vessels for hydrogen storage under pressure ranges of 350 to 700 bar. And we also look at hydrogen sensing, because whenever we store hydrogen in such high pressures, sensing hydrogen leakage is an important area. So we would like to focus on those areas, and we are working on those lines as well. And as I said, CO2 capture and conversion is one of the areas that one of my colleagues also works, and we have also taken up some bit of activities in that, developing catalysts for conversion of CO2 to various value-added chemicals. And finally, as a material chemist, our primary motto is to focus on various new material developments, ranging from graphene to other 2D materials and so on. So keeping that as a primary area, all other are ancillary areas which contribute to the development of the country and the scientific world in general. Coming to the actual topic of today's discussion, as we all know, hydrogen is being industrially processed through steam methane reforming or natural gas reforming. Steam methane reforming or natural gas reforming is an established area, and for years together, most of the industries across the world have already made this process an industrially viable process. In this direction, although hydrogen is effectively being utilized and produced, it is not a CO2 free area. When we say not a CO2 free area, there is a lot of carbon emission associated with it, and hence it is difficult for industries to cut down the CO2 emission and subsequently go ahead with the green process of producing hydrogen. On the other hand, the coal gasification is a process which has taken up a good amount of industrial establishment, and the process is already very well saturated in the industries. When we talk of coal gasification, coal is gasified and converted into syngas, wherein the syngas produced comprises of hydrogen, carbon monoxide, and traces of carbon dioxide. So in this gaseous mixture, hydrogen is separated either using a pressure swing adsorption process or a membrane separation process. I'm going to come to these details in the next slide. But in parallel with coal gasification, biomass is an alternative that is being looked upon, because biomass produces a good amount of hydrogen through the gasification process and also produces less amount of carbon compared to the coal gasification process. When we look at the steam methane reforming or the natural gas reforming and the biomass gasification process, comparatively biomass gasification is more reliable and offers a reduced CO2 impact on the environment. On the other hand, we have processes like electrolysis through renewable energy sources like solar, wind, and other electrolyzer-based hydrogen production processes, where hydrogen production is labeled with different colors like green, yellow, pink, and so on, depending on the nature of its production. If it is produced through a renewable energy source connected electrolyzer system, then it is called green hydrogen. If a gasification process is connected with carbon capture and utilization system, then it is called a blue hydrogen. And the color doesn't actually signify the color of hydrogen, because hydrogen, as you know, has no color and is intentionally called devil's gas, because neither we can see it nor smell it. So while various processes of hydrogen are being developed parallelly across the globe, a lot of impetus is given for hydrogen production, whereas less focus is given on the separation or the storage of hydrogen. We all know that hydrogen, of course, can be produced by various established and other newly upcoming technologies. However, in order to store the produced hydrogen, where do we go? What are the kinds of technologies do we have in order to address this storage issue? When we talk about the storage issue, it is important for us to make sure that hydrogen is stored in a safe and secure manner so that it can be transported effectively. But before going into the details of the storage, I would like to touch upon the fundamentals of the membrane component. As I said, during the gasification process, when coal is converted into syngas comprises of carbon monoxide, hydrogen, and carbon dioxide. And in this process, either membrane is used to separate hydrogen, or pressure swing adsorption processes are being implemented. In parallel to pressure swing adsorption process, there are also other processes called electrical swing adsorption and thermal swing adsorption processes, which are rarely used but have been tested and implemented previously. But the most established and the convenient process which is currently being implemented in most of the industries is the pressure swing adsorption process, where we have a molecular sieve or a material that can absorb hydrogen and release it so that it effectively absorbs hydrogen and then separates it out from other mixture of gases like carbon monoxide and carbon dioxide. Whereas on the other hand, we have membrane-based gas separation processes where industrially viable membranes are being fabricated and brought into the environment of the gasification process, where hydrogen being only 2.8 angstrom in size is very small in nature, and hence the kind of membrane that we use should be non-porous in nature. So when we say or use the term non-porous, it effectively means that their pore size is very small, only to facilitate hydrogen to penetrate through it or pass through it, and not allowing the other molecules to pass through the membrane. But unfortunately, what has happened is most of the industries which tried and used membranes for gas separation did not really scale it up and continue the usage of membranes because of various problems associated with the membranes. One of the foremost problems associated with such membrane-based gas separation process is the membrane fouling, the durability of the membrane, and frequent requirement of changing the membrane due to its rupture and other environmental issues associated with bringing the membrane into high temperature environments. So in that process, we till today do not have a industrially viable and usable membrane that can effectively go into the gasification process and confidently compete with the pressure swing adsorption process, where the gas separation membranes can stand out and say confidently that I can replace the pressure swing adsorption process. But in order to address this particular aspect, we are in the process of developing such industrially viable membranes. I'm going to show you some of the results associated with it. And these industrially viable membranes are rugged enough to match up to the requirements or conditions of the industrial gasification process. And in due process, they are able to separate out hydrogen effectively compared to any other gas mixtures. So in any mixture, for that matter, hydrogen is effectively separated through those processes, and we get pure hydrogen gas on the other end. So here in this slide, you can see how different characterization results of hydrogen are being showcased, wherein we have a laboratory setup where we make use of a flat sheet membrane, which comes in contact with the hydrogen gas or a mixture of gases, because in this particular case, it is a simulated gas mixture where we have a combination of hydrogen and CO2 or hydrogen and methane together. And since we are testing it out at the laboratory environment, we can only use the simulated gas and not the real gas that is coming out of the gasification process. So in the simulated environment, we place the flat sheet membrane in a membrane cell and feed the gas. So as the gaseous mixture passes through the membrane separates out only hydrogen and offers it as a permeate. So these hydrogen molecules that are coming out of the membrane effectively permeate through the membrane through the small pores that are available on the surface, and separate hydrogen from the rest of the gaseous mixtures under a certain vacuum environment. When we tested this membrane, these membranes are typically mixed matrix membranes, which comprises of nanoparticles as well as polymer materials. So the combination of the polymer and the nanoparticle effectively brings about the hydrogen separation efficiency to a great level. We also performed the mechanical characterization studies in order to study how durable these membranes are and what are the strengths of these membranes. And as you could easily make out from the results, the graphs that are shown here, the strength of the mixed matrix membranes when nanoparticles were introduced into the polymeric surface, the strength of the membrane gradually increased. And on the right-hand side, you can see the cross-sectional image of the membranes where different porous surfaces are being shown. And these cross-sectional images clearly indicate that how the pores are formed on the surface, and the nanoparticle facilitates the penetration of hydrogen or the separation of hydrogen effectively through the membrane. So when we carried out these gas separation studies with respect to various percentage variations using a mixture of hydrogen, methane, and hydrogen carbon dioxide, we noted that compared to the control membrane, that is only a polymer membrane without the nanoparticle infused into it, the difference that we could make out was the separation efficiency was found to be 4:1. That means 4 molecules of hydrogen could pass through, and hardly 1 molecule of methane or carbon dioxide could pass through it. So in terms of the efficiency, this is very well noted in terms of the percentage efficiency of 4:1, and the kind of separation effect that could be brought about in terms of hydrogen is almost much higher than the traditional palladium-based gas separation membranes. Because initially, when we carried out such separation studies, we identified that the palladium membranes, which are considered to be the standard membranes that were previously used in the industries, used to show an efficacy of 38 barer separation efficiency, whereas our membrane showed a separation efficiency of about 58 barer. So there is a significant difference in the separation efficiency while using palladium-based membranes, which are expensive in nature, whereas as an alternative, we used magnesium nitrate, MgNiO2 nanoparticles in order to infuse these nanoparticles into the polymeric environment. And these materials being conducive with the polymeric material supported and facilitated the separation of hydrogen very effectively. So based on the results that we obtained, we also came up with 4 different mechanisms of hydrogen separation, where permeability could be one of the factors where, depending on the pore size of the membranes that were created due to the reinforcement of the nanoparticles into the polymer matrix, the separation efficiency could have been very good or better in terms of separating hydrogen. On the other hand, the introduction of the nanoparticle and the polymer and their blending together in a conducive manner enhance the separation efficiency, where this compatibility of both the polymer and the nanoparticle came into effect and enabled the separation of hydrogen. On the other hand, one of the interesting aspects is that the reduced tortuosity. In this aspect, the hydrogen passing through the membrane can easily pass through the membrane in the most easiest way, rather than following a different path which is more cumbersome and complicated. Whereas the hydrogen separation could have also been effective because of the affinity of the nanoparticles towards hydrogen gas. As you know, magnesium and nickel both are having good affinity towards hydrogen, and hence, because of the presence of these highly effective magnesium and nitrogen atoms associated with this nanoparticle, they will enable, they probably may enable the separation of hydrogen through the membrane in an effective manner. Similar to the separation efficiency, as I mentioned earlier, we also work on development of various electrocatalysts. And one such electrocatalyst that we have worked on and developed is sodium iron disulfide, NaFeS2. One of the most interesting aspects associated with this material is that this material, although appears to be a new material when we actually started working on this and developed this material, it was developed by one of the European groups way back in 1960s. So at that point of time, only basic characterization of XRD and SEM was performed on this material after it was synthesized using a simple hydrothermal process. And nothing much was done beyond that. And while going through the literature, we came across this interesting material, and we tried to reproduce the material in our laboratory. Fortunately, we were successful in synthesizing the material effectively, and we initially started with testing this material for the effectiveness in terms of photocatalytic degradation of pollutants. When we observed significant degradation abilities of this material, we wanted to expand its application to electrocatalysis and study how good the material is in terms of producing hydrogen or enabling hydrogen production. So in that regard, we also carried out both hydrogen evolution reactions and oxygen evolution reactions on this material, and were able to note that the efficiencies of the material was quite significant, because the over potentials at which the hydrogen was produced, the 370 millivolt at 200 milliamps per centimeter square, is quite significant compared to the industrial standards of platinum and iridium. As you all know, the platinum and iridium are very expensive materials, and the whole world is up to replacing those two materials and find a suitable alternative. So when we pitch this particular material as an alternative material to platinum-based electrodes, we had a lot of interesting questions by the reviewers when we submitted it for publication, but we were successful in answering those questions and finally got them published in Chemical Engineering Journal. And we also performed, along with the experimental studies, we wanted to substantiate the experimental work with DFT calculations. And these DFT calculations also helped us in determining the OH minus group as the rate determining factor, which is effective in absorbing absorption of this particular material. And while elucidating the kinetics, it is quite evident that the Tafel slopes clearly display 31 millivolt per dec for the electrocatalyst developed. And this is a clear indication that the material behaves very positively for both hydrogen and oxygen evolution reactions. On the other hand, we also try to come up with another material, which is cobalt selenide in combination with graphite carbon nitride. And this combination, although a couple of reports were earlier available in terms of battery material electrode studies, there were no such reports associated with the hydrogen evolution reactions. When we took up this material and wanted to explore it, we did not limit ourselves to only electrocatalytic applications. We performed the photocatalytic applications as well as the supercapacitor applications associated with it. So when we carried out 3 different applications, we were able to figure out that the material is a multifunctional material. So when the efficiencies of this material proved to be much higher in all the 3 applications, we could project this material as a multifunctional material for various applications rather than limiting its application to only one area. So while developing these materials, we were also subjected this for photocatalytic degradation of bisphenol, where we obtained 92% and higher degradation efficiencies. And we also found that 380 millivolt current densities at 15 milliamps per centimeter square for OER and HER, and specific capacitance of 153 Faraday per gram for the supercapacitor studies. The most important and interesting aspect is that in spite of using this as an electrode material and after running it for several cycles, the retention of this material was greater than 90% even after 3000 cycles. So this actually clearly gave us confidence and strength to say that this material is good enough to compete with various other materials and can act as an effective multifunctional material in order to make sure that this application is not only limited to one specific application, and we need not develop new materials for newer applications. Rather, one material can act as an effective material for various applications in parallel. Now, coming to the actual part of the work where our strength lies is developing lightweight composite cylinders for high pressure hydrogen storage. This is one of the interesting areas which I think most of the European and American labs have already initiated some works, but in India, we were the first group to initiate some of the activities associated with the development of this particular material and the technology. There are a few industries and national laboratories in Europe and USA who are specifically experts in developing such type 4 hydrogen storage materials, pressure vessels for storage of hydrogen under high pressures. But unfortunately, in India, there were no such technology apart from a metallic cylinder that is being used for hydrogen storage applications. But since metallic materials for hydrogen storage undergo severe hydrogen embrittlement, that was not the only solution that we could bank upon. So in order to overcome the complications associated with metallic interaction with hydrogen and the hydrogen embrittlement associated with it. Apart from the hydrogen embrittlement, we also faced difficulties in terms of the bulky nature and the heavy weight of the cylinders, which were difficult in transporting these cylinders to different places. So transportation became a major issue. In order to overcome these deficiencies, we thought, why don't we start working on this technology and develop indigenous materials that can eventually help the industry, both in the automotive sector as well as in the chemical sector, which can take up these lightweight composite cylinders to store hydrogen and effectively use them in their applications. So in that direction, we wanted to move ahead and try to come up with new liner materials. But eventually, as we did not have any previous associated experience in this, we had to start from the scratch and carry out studies right from the beginning, right from identification of the material itself. So in that process of simulation and the material identification, the material design process and the structural analysis had to be performed in order to make sure that we go with the right set of material, because not every material is compatible with hydrogen or capable of storing high pressures of hydrogen or the effects associated with hydrogen when compressed under high pressures. So simple polymeric materials are not effective. So we need high density polyethylene materials, HDPE materials, in order to suffice to these requirements. So in this process, we took up additive manufacturing as one of the application tools in order to design, define, and carry out some of the simulations and then 3D print cylinders effective for our specific applications. So in that direction, we were able to overcome many of the material associated challenges and could reduce some of the problems that we could face in the initial stages. When I was talking about type 4 hydrogen cylinders, there are 4 different types of cylinders that are identified in the commercial sector. Type 1 is a metallic liner, which doesn't have any kind of overwrapping on it. It can be either steel cylinders or aluminum cylinders. And it can also be overwrapped with some glass fiber composites, which is called type 2 cylinders. And subsequently, aluminum liner material or titanium liner materials overwrapped with carbon fiber composites are termed as type 3. And finally, a polymeric liner material, which is encompassed or covered with a carbon fiber composite, is called type 4. There are new R&D developments that are happening in type 5 category as well, where there is no overwrapping on the surface of the liner material. The liner material itself will be strong enough and capable enough to hold the hydrogen under high pressures of 350 to 700 bar. When we came up with the material design of ABS, that is acrylonitrile butadiene styrene, and tested it as a basic polymeric material, ABS was not capable enough to hold high pressures of hydrogen. So in order to make it suitable, we blended 10% of carbon fiber into ABS matrix and then tested the efficiency. When we carried out some of the preliminary property analysis, such as density, Young's modulus, and yield strength, we were able to identify that ABS improved its properties gradually with the addition of carbon fiber, whereas titanium, being a metal, had its own strengths and weaknesses as well. But carbon fiber individually is much more capable and multifold stronger and offers a better performance compared to ABS. But carbon fiber, being a very costly and expensive material, cannot be directly applied for making such liner materials. So we had to find an alternative in order to substitute the carbon fiber with polymeric materials, and a combination of both the HDPE polymer and carbon fiber could even provide better results. So while developing this modeling and simulation activities, the initial mesh models were prepared using ANSYS, and the structural analysis associated with these cylinders were carried out. While developing these cylinders, one of the interesting aspects we also tried and tested is that why should the cylinders be actually cylindrical in nature? Why don't we change the shape of the cylinder and try to come up with a different form of the cylinder? The basic problem associated with such change in the design is that when the pressure is applied within the cylinder, the most vulnerable part of the cylinder is the sharp edge associated with it if we change the structure oriented with it. Those sharp edges, like a square or rectangular model, will eventually cause ruptures on the surface of the cylinder, and due to which there is diffusion of the gas from the liner material. So we could not actually overcome the change in the structural design, but effectively we could model the cylinder in such a way that there is a bit of change in the supportive structures that we are providing within the cylindrical model. And I will show you in the next slide how interior strengths are increased by introducing new aspects associated with the developmental process. In the table given below, you can also see that there is a variation in the factor of safety when we move from type 1 to type 4. These factor of safeties are one of the important aspects which actually make the cylinder tell us whether the cylinder is safe enough to be used for its practical application that it is intended for. So when you look at type 4, 2.48 is the factor of safety to which the cylinder has to be tested in order to ensure that the cylinder will actually abide by the norms of the industry and meet the requirements of a safe, secure, and a strong cylinder which can hold such high pressures of 350 to 700 bar. So in principle, if you are looking at a cylinder which can hold hydrogen under high pressures of 350 bar, 350 into 2.448 times has to be the actual testing parameter, or the pressure at which the cylinder has to be actually tested, and that will actually give us whether the cylinder can maintain or bear the required pressures at that level. And if it passes through that, then there's nothing beyond that, and the cylinder will automatically the material will automatically qualify to be used as a type 4 cylinder. When you look at the weight reductions as well, there is a significant amount of weight reduction from type 1 to type 4. And in type 3 also, there is 38.5, whereas in type 4, the kind of material that we use matters a lot. And subsequently, 39.2% or nearly 40% reduction in weight compared to type 1 is quite evident. And this makes the cylinder comparatively less weight and easily transportable. So during the design and developmental aspects, we were able to identify how the cylinder can be strengthened. There are two ways associated with it: by providing new support structures within the cylinder, or by increasing the layer thickness of the cylinder. Increasing the layer thickness of the cylinder is not a viable option, because that involves a lot of polymeric material, and the thickness of the liner material eventually increases. With the increase in the thickness of the liner material, the weight of the cylinder also gradually increases. So in order to counterbalance the weight and the number of layers associated with the thickness, we introduced some kinds of rib-like structures within the cylinder. So, and we studied how a rib-introduced structure and a non-rib structure differ in terms of the design aspects and the ability to bear the necessary pressures. And we realized that the structures, cylinders with ribs perform much better because of the internal structure and the support that it could provide and offer the necessary strength to the liner material compared to the ones that did not have any ribs. So in terms of their performance analysis, we carried out FEA simulations and understood the Von-Mises stress and the displacement associated with such rib and without rib oriented structures. And by looking at the FEA analysis images, you can clearly make out that how different colors indicate the kind of stresses and the displacement that the material has undergone. It is not about the stress and the displacement that the material can undergo and bear, but it is about the ability to come back to its original shape after undergoing such stress, strain, and displacement. So while carrying out these studies, as I mentioned, by the introduction of 10% carbon fiber to ABS, the percentage efficiency of ABS material increased by about 70%, which is a significant number. And with the increase in 70% strength of the material, this qualified actually to be used as a liner material. In this slide, you can clearly see how the combination of ABS and carbon fiber cylinders with rib structures evolved during the initial design and simulation phase and the liner production and its different testing and what is the current state of the cylindrical development. The initial images show that the internal rib structures are being provided within the cylindrical models, and the rib structures, although they are evident in the simulated model, but when actually they are printed using a 3D printing system or a FDM process, you don't actually get to see the ribs within or on the external surface of the cylinder. But obviously, by the introduction of the ribs are present within the surface of the cylinder. We have not cut open the cylinder as such in order to show that, but those ribs are definitely present within the cylinder. The white cylinders that you see are the plain ABS materials that were initially printed in order to test the strength of these liner materials, whereas the black one that you can see on the right-hand side is the carbon fiber blended ABS, which clearly showed that there's a significant color difference as well as the material's strength increased drastically. There were other materials that we also printed as a showcasing prototype or a dummy models where different volumes were prepared and those were mechanically subjected to their tensile property analysis as well. In the bottom of the right-hand side, you see two different cylinders coated with some colors, and these are specifically coated with thin layers of metallic particles, especially nickel and copper. When you look at these coatings, you may think that why do we need such coatings when carbon fiber is already present as a supporting and a strength enhancing material? As we are 3D printing these cylinders, irrespective of however small the layers are optimized, there are minute micropores that are present between the two layers that are printed during the process of 3D printing. So in order to cover up those layers, we had to introduce this metallic coating of nickel and copper onto the surface in order to ensure that the gas doesn't diffuse out of the cylindrical pores that were 3D printed. And in this journey, we also carried out some aspects of design orientations, considering three different materials like ABS, nylon, and PEEK. And in the kind of orientations like the circumference oriented or the other components associated with it, we could identify which of the three materials were more suitable for such studies. Although PEEK appears to be much stronger compared to nylon and ABS, PEEK is more of a rigid material that cannot be easily used for 3D printing applications for specifically the printing of cylinders. But ABS and nylon being more compatible with carbon fiber was more suitable for such 3D printing applications, especially for to be used as a liner material. And in that journey, we could identify, although there were some amount of displacement seen for nylon and ABS also, nylon appears to be a more suitable material. Nylon, when we say nylon, it is nothing but polyamide materials, and eventually the circumferential patterns or the hoop stress associated with the cylindrical liners were the ones that play a significant role in bearing the required pressures within the ABS and associated nylon or PEEK materials. So finally, we could come to an understanding that both nylon and ABS were able to make up to the requirements of this high pressure hydrogen storage, and helped us in giving a better understanding when we carried out the drop test simulations as well. So in this drop test simulations, we were able to understand that the carbon fiber overlapping on the surface of the liner material was able to absorb most of the stress or the display damage dent that is caused on the surface when it is dropped from a height of 10 feet through the simulation process. So the carbon fiber also plays a very important role being overwrapped on the surface of the cylinders. These images are typical examples of initial coating tests that we carried out using nickel and copper through electroplating process, where we could identify that sheet resistance played an important role, where nickel had a much lower sheet resistance compared to copper, and nickel has a tendency to undergo embrittlement while interacting with hydrogen, whereas copper will not interact with hydrogen and doesn't have to undergo hydrogen embrittlement, as copper is not so interactive with hydrogen. So understanding these aspects gave us a lot of information, and also took us to a slightly further analysis in terms of structural and drop simulation analysis as well, where we performed some of the deformation studies and try to understand how much of induced stress was being laid on the surface of the liner material, and what are the ratios at which these variations could really impact the cylinder to a significant level. Compared to the type 1, type 4 underwent higher deformation being a polymeric material, but it was able to sustain the deformation and come back to its original form after the stresses were released, and nearly 40% lower in weight was quite good enough in order to make sure that the cylinder is reduced in weight and could be easily used for transportation as well. And we also performed some a crash test through simulations in order to understand how the cylinders behave when a vehicle traveling at a speed of 80 km/h hits onto a head-on collision, comes in head-on collision with a opposite vehicle and hits with force. What kind of variations do these materials undergo? And in all these studies, it was quite evident that type 1, although it was not much deviated from the actual structure, but could easily undergo deformation and rupture the cylinder and cause a lot of damage compared to type 3 and type 4. And overall, type 4 came to be a better performer with despite the crash test being subjected on all three, the type 4 evolved to be a better material compared to the type 1 and type 3 materials. These are some of the images that we have 3D printed and carried out some of the mechanical studies associated with these 3D printed materials, and the carbon fiber wrapping that we actually manually tried to do it initially in order to make sure that the carbon fiber wrapping on the surface could hold on to the cylindrical liner materials. So before concluding, I would like to place on record my sincere thanks to all my students who have contributed significantly to various activities associated with the hydrogen applications ranging from production, separation, storage, and eventually to all the funding agencies that have supported me over my past 12 years of research experience, and have finally brought me to this distance, contributing effectively to the scientific field. Thank you so much, and I'll be happy to take up any questions if there